So first of all, thank you very much, organizers, Nihar, Sayantan, and Santosh. Before I start, I would like to tell you that I am the only person between you and your freedom. Okay, so I will try to wrap it faster. I'll not bore you much. Okay, so I'll talk about heavy quark dynamics in a near equilibrium hot QCD matter.
You can make the freedom as in thought.
Yes, yes. Yeah, that's good one. Okay, so here's the outline. I'll just present some motivation, although I think a lot of things have already been said regarding that. Then I'll quickly go to transport framework, and then I'll touch upon the anisotropic aspect of hot QCD medium and how the drag and diffusion of heavy quarks are getting affected due to that. And then I'll also touch upon some heavy quark radiation and its impact on the heavy quark drag and diffusion coefficients within this framework. Okay, so I think I'll start by saying that be prepared for a journey, but don't expect a destination. So I may not be able to answer your questions concretely because this is ongoing work and I left it 2-3 years ago and I'm again going to pick up it. So, okay, so there is some gap, but yeah, doesn't matter. So, okay, I'll just go through the motivation again, just for the sake of completeness. So, heavy quarks such as charm and bottom are hard probes that are created in the initial stages of heavy ion collisions. So, due to their mass, larger mass, their thermalization time is longer. So, they basically record the entire space-time history of the QGP. So, you have already known from the talks by Adiba that the evolution can be modeled by Boltzmann equation and in the small momentum transfer limit that goes to Fokker-Planck framework. Okay, so the key observables regarding heavy quarks are nuclear modification factor, flow coefficients, although I'll talk about a bit on RA finally, but this part we have not touched upon. So ultimately we have to extract them from this framework and finally compare them with the experiments. Okay, so although that part, that's why I said that don't expect any destination. So this is in that context. Okay? Yeah. Yes. Yes. Yeah. So these observables depend strongly on, okay, the observables that I talked about here on heavy quark drag coefficient and diffusion coefficient. So we will basically try to understand them in the anisotropic medium. Okay, so a few things about anisotropy. So anisotropy could be, momentum anisotropy could be there from the early stages of the collision, and even during hydro, you know that the spatial anisotropy transfers to the momentum anisotropy. So in that sense, momentum anisotropy will be there throughout the space-time evolution of QGP. So for a momentum anisotropic distribution, this is, okay, this FP is an isotropic distribution function. That's why I have just written the mod here. So the distribution is anisotropic. And this will affect screening properties, transport coefficients, and all kind of, observables that are possible there, okay? And this is one model of momentum anisotropy where you can just stretch or squeeze the isotropic distribution function. You can have oblate or prolate shape depending on whether this size is positive or negative, okay? So, and this n is the direction of the anisotropy. So in that way you introduce anisotropy. If you remember, Najmul already talked about anisotropy and he told you like how the heavy quark self-energy, how the gluon self-energy basically is decomposed in the case of anisotropy. So what kind of tensor decomposition will be there? So this is in line to that, but now in the context of heavy quark drag and diffusion coefficients. Okay, so there are some walks that I could record. There are many other walks also, but I could only record them. So there is, this walk started from, anisotropic flow, olethro-Vosolin. Then early time anisotropy in non-equilibrium QGP, I think Strickland worked out some of these things. Then the anisotropy hydro was discussed by a couple of groups. Then people also looked at plasma and anisotropic momentum broadening. Then dileptons have been studied. There are transport models where anisotropy has also been included. The heavy quark diffusion in strongly anisotropic plasma was studied in this particular reference. Then there are a lot of works on heavy quark potential in anisotropic QGP. I have just taken first few, okay? And then there is another part, I think Najmul talked about Weibull instability, chromo-Weibull instability. So the physics of chromo-Weibull instability can be modeled in a diffusive Blasso equation, and then that leads to something called the anomalous transport. And this process, suppresses the transport coefficients usually. So this effect was studied in QED plasma by Dupree in 1954, and this was some sort of like chromo version of the same work. And we also looked at this, and this could be one explanation for small eta bias. Okay, that may not be the all story, but this, because of the huge suppression in the transport coefficients, you could explain small eta bias. Okay, so this has been looked at. So in this talk, I'll talk about how does the anisotropy affects, okay, I forgot that word, affects drag and diffusion felt by the heavy quark. Okay, so this is the question that I'm going to discuss based on these two works that we wrote in 2022 and the application of that in 2023. And this work was done with Santosh, Avdesh, and Manu, basically. So it is primarily Manu and Avdesh who worked out all the mathematics, and me and Santosh helped them. All right, so, okay, let's start. Okay, this is again for the sake of completeness because this has already been discussed by Adiba. So heavy quark dynamics can be understood in terms of the Fokker-Planck equation. This can be obtained in the small momentum transfer limit, as I said earlier. So just look at the equation number 1. So the first term is the drag force. The second term, Bij, is the momentum diffusion tensor. And these transport coefficients capture the interactions of the heavy quark with the light quarks and gluons that constitute the QGP medium. Okay, so our aim is to understand the AI and Bij in the presence of anisotropy. Okay, so this is the expression for the Aij. So this is for the collisional processes where heavy quark, light quark scattering happens, and then this is in the small momentum transfer limit. Okay, so this is the AI that can be written in terms of phase factor, and then this is your scattering amplitudes and all that, and this is the transport part, basically the distribution function. So you can write down AI in terms of this expression, and this we are calling, this is represented in terms of this double brackets. Okay, this is just the average value that is computed in this particular way. Similarly, this Bij is basically this momentum diffusion, and this is written in that form, and you can again write it in that particular form. All right. And then, okay, this is what I said. So these transport coefficients have a phase factor, interaction, and transport part. All right, so this is again the standard one for the isotropic case. So AI can be written in terms of this A0, this coefficient, and Bij can be written in terms of B0. Because we have only one, vector available, that is the momentum of the heavy quark, P. So we can construct a rank 2 tensor like that. So that's why there are only 2 terms here. Okay. So once we have anisotrope, okay, then this is just the definition, and this is like, you can in general write down the average of any quantity. This has already been written there, but it is written in the combined form now. So you can replace this Fp by this P minus Pi or P minus Pi minus P, and then the other one, like, okay. So, and all right, this is just some mathematics. Now let's look at how these drag and diffusion coefficients looks like in the case of anisotropy. So clearly now you have 2 vectors. One is the direction of the anisotropy, other one is the momentum vector. Okay, so now you can construct rank 2 tensor, rank 1 and rank 2 tensors with the help of these 2 vectors. So the first thing we will do is that we will construct a vector that is perpendicular to the momentum of the heavy quark. So this is what we have constructed. We will call this n tilde. And then now our drag will have 2 parts. One is along the momentum of the heavy quark, other one is along this ni tilde that is perpendicular to the momentum. So this is the decomposition for the drag part. And then you can, again write it in terms of these double brackets that I talked about. Similarly, okay, this is again the same expression. And so what we have done is that we have chosen the F to be F plus delta F. All right, so in general, we cannot do that, but we are working in the small anisotropy limit. So we can expand our F in terms of F naught plus delta Fk. So that delta F, so if we write down things in that way, this average value will also be decomposed like this. So this is kind of the linear term, and this is the term without anisotropy. So I can write it in this particular form. This is the simplification that we did. We have to do it in the general anisotropy, but we don't know whether the integral will be solvable or not. But okay, in the weak anisotropy limit, this is the decomposition that you can have. And similarly, the anisotropic drag coefficient will have that decomposition, because there will be this part that will be A naught, this isotropic part, and then the anisotropic part is entering in delta A naught. So in that way, you will see that all the transport coefficients will have this kind of decomposition. Okay. So similarly, I can write down the Bij, the diffusion tensor. Now you can construct this rank 2 tensor with the help of this P and N tilde. So this is one that is perpendicular to P, then parallel, then this parallel and perpendicular. No, not parallel. So this is like P and N. You can construct a second rank tensor due to that. So you will have like B1, B2, B3. So basically B2 and B3 are the new transport coefficients. Okay. So this is in the case of isotropy, and in the case of anisotropy, you will have 2 more transport coefficients, as you can see from here. So in total, you have 1 more drag coefficient and 2 more diffusion coefficient. And Adiba's work is like concentrating on only A0 and B0 and B1 basically, because I think the viscosities has been introduced through delta F, and this standard transport coefficients has been computed basically. But in general, in the case of anisotropy, these many drag and diffusion coefficients will be there. And you need to compute all of them. They may not be significant in some range of momentum, but you have to compute them and then see how do they look like. Okay, so then there are like these 4, and they need to be computed like this. And then we concentrated on how to compute them. So the most important point here is that the angle between the momentum of the heavy quark and the anisotropy, that is one parameter that will sustain at the end, and then all the results will dependent on that. That we are calling theta n. All other variables will be basically integrated out at the end, and the strength of the anisotropy. So xi and this theta n, they will sustain at the end, and they will contribute to the coefficients. Okay. Again, this is some mathematics that we have to do. So if you look at these expressions, you will see that this P dot P term, of course, that will contribute, but the anisotropic part is entered in this P prime dot N tilde. So we have to compute this term, and that will contribute to all the anisotropic coefficients. Okay. So this I'll skip, I'll not bore you with that. That is what I said. So the strength of in the presence of anisotropy, 2 independent drag coefficients will be there. One is parallel to P, other one is along the direction of the anisotropy. And then there will be 4 diffusion coefficients. 2 of them are there in the case of isotropy also, 2 more. And the relative angle between the P and the N. Okay. So the strength of the anisotropy and this angle will finally tell you like how much in the small anisotropy limit this particular anisotropic effects are contributing. Okay, so this is all about the mathematics in this part that we did. Then let's go to the results. So this is like your drag coefficient in the case of anisotropic medium is A0 and A1. So A0 can be decomposed as A0 isotropic plus delta A. So just look at the relative contribution of this term with the A0. So you can see that, okay, this is for the different value. Okay, anisotropy, we have not moved much, 0.2 to 0.3. I think if you just look at hydro and look at the relative, PL by PT, that is of these orders like 0.2, 0.3. So these numbers are motivated from there. So you see that there's a large there's a theta dependence, and this chi dependence will not be much here, as you can see, because there's not much change in chi. So what you will see is that the angular dependence is much more pronounced in the low momentum region. Okay, so this is for delta A by A0. This is A1 and A0, right? So we are just looking at this quantity also. So here you can see that basically the effect is again important in the low P region, and in the high P region, this is going to 0. So if you are working in low P, this will contribute. Otherwise, this will not contribute in the small eta limit. And this is the theta values that we have taken. So this is about the drag that you have seen here. Okay, so the same thing that you could see here. So these are the temperatures that has been taken here, as you can see. And then, okay, so this is about the diffusion. So this is delta B0 by B1, because all the transport coefficients are decomposing like their isotropic value plus the corrections from the anisotropy. So this is what you can see again at low. Okay, this is B0. B0 behavior is slightly different. What I could say is that the anisotropy is affecting it up to 20%. Okay, so it is 20% to 12%. We can think in that way. And similarly, this B1, delta B1 by B1. So this B0 and B1 are there also for the isotropic case. But then we just want to know how does the anisotropy affects. So this is what you can see. You can resolve the angular dependence, but I think the magnitude will not contribute much at this moment. Okay. So similarly for the other transport coefficients, for B1 aniso by B0 aniso, I think you cannot resolve it much. B1 is not much sensitive, as you can see, like it's very close. For B2 and B3, again, the low momentum region is important. The effects are more pronounced in the low momentum region. So until now, what we learned is that in the small anisotropy limit, the transport coefficients are affected in the low momentum region. And of course, there are more transport coefficients as compared to the isotropic case. Okay, so then this is about just to understand the transport coefficients while including the elastic collisions, 2 going to 2 collisions. Now, we also looked at this for the case of radiative processes. And of course, this is the process 2 going to 3. And then the fifth gluon, so the gluon that is radiating here is basically soft. Okay, so we have taken it in the limit, soft limit basically. So this is the standard thing that was talked by Adiba earlier. So this is the dead cone factor, which is obtained whenever the formation time of the gluon is much more than the time between the two scatterings. So in that case, the scatterings will have destructive interference, and then that will have the LPM effect basically, and then there is dead cone effect also there. Okay, so all that will combine to give you the contribution to the transport coefficients in the anisotropic case. So again, what you will realize is that the isotropic and anisotropic case, this kind of decomposition will work.
Like the dead cone effect is completely absorbed in this 1 plus.
Yes, you're. So, all right. So then this is the decomposition that could be looked at in this case when there is a soft gluon emission limit, and this can be again generalized to the anisotropic case. Okay, so the thing is that this is near equilibrium situation. That's why you are just generalizing these expressions to anisotropy. If the anisotropy is strong, then you will not be able to do this decomposition. And you cannot just replace F by F naught plus delta F. So that is one problem to generalize this whole approach for the general anisotropy. In the strong anisotropy limit, you can still do that because then the perturbative parameter will be 1 by chi instead of chi. Two extremes you can take care of, but intermediate region, probably this all will not work. So you have to relook it. Okay, so we included all these effects, but even the dead cone effect is basic. So this LPM effect is also introduced in a very gross way, as you can see. There's a theta function that is there. So it's a very gross way to introduce this thing, and it is done in those works, and we didn't relook it. I think this also need to be relooked for the anisotropy case. For example, if you want to study this whole thing in the presence of the magnetic field, you will have to relook this whole formalism. You cannot just use it. Okay. So that is one motivation that we have now, and we will try to relook that. Okay. So then, as I said, you can in this limit you can just again look at the transport coefficients in this particular way, the isotropic part plus the anisotropic part. And if you do that, then you can, just compare the collisional and the radiative effects within this simplified version. So your drag, okay, now there are change of notations because these are two different works. So this gamma is like your A, okay? Gamma is like A naught, gamma 1 is like basically your A1 or something like that, and then, okay. So here we just plotted the collisional contributions with isotropic whenever it is written without delta Fk, that is isotropic. And okay, so these are the parameters that has been fixed. So they are fixed because we want to have some resolution, okay, so that we can distinguish between them. So this is the parameter that has been chosen. So the drag coefficient as a function of P is plotted here. As you can see that if you include the radiative effects, the drag is decreased, like it is suppressed in a way, okay. The heavy quark will suffer less drag if you include radiation. But, okay, but the magnitudes are maybe within few percent, maybe 10, 15, 20%. Similarly, for this D naught is like your B naught, this diffusion coefficient, the similar thing that you can see here. Here also you will see that, okay, if now you look at the anisotropy, again the same thing you are observing here. It is more pronounced at low PT, low P, okay? So then we have looked at other transport coefficients, like gamma 1. Gamma 1 is like A1 now, D1 is like B1 now, so their relative things has also been studied. So you can again see that all the results are affected by the direction of the anisotropy. Okay, what is the angle it will make with the direction of the heavy quark momentum? So that is the most important parameter here. Anisotropy is not moved much, okay, 10%, only 0.2 to 0.3. So this low momentum region is important. Again, it is highlighting the same thing. So again, this similar kind of study has been done here in the case of radiative corrections. So the D1 relative, okay, so D naught is also anisotropic. All the coefficients have anisotropic contribution. So D naught can be written like D naught plus delta D naught. So in the small anisotropy limit. If you just compare like D naught anisotropic with D1 anisotropic, this is what you get. So, and of course, all of them will go to the isotropic limits when you will take xi going to 0 limit, okay? So that we have checked. I mean, there is no problem in that. Anyway, only the contributions are always linear, so you can switch off that term anytime, right? So here also you can see that the low PT limit, low PT region is important for you. Okay, so I think this is all about the radiative versus collisional corrections. Now we have also looked at this particular expression, the simplified. This is also a simplified expression. So this A naught is also only entering here as far as the energy loss concerned. So A naught anisotropic has this delta A naught part that is coming out from small anisotropic limit. In that way, anisotropy will also basically affect the energy loss. Okay, so the energy loss has been plotted here as a function of P. Again, in the low P limit, there are basically corrections that are from the anisotropy. This is all done in small anisotropy limit. So whatever is here is in that. Even within that approximation, the angular dependence is quite significant. Okay. So now finally, we also looked at RA. Again, this is with a lot of approximations. I mean, that's why you will see that we will not compare this RA with the experimental number. To compare this RA with the experimental numbers, we will need to look at this formalism in the hydro background, full 3+1D hydro background, and then calculate RA, V2 and all that. Then maybe we can compare. But at this moment, we have just, make some rough estimates, okay? So you know that the dynamics of the heavy quark will be governed by Langevin equation, and this all has been discussed. I think this was, somebody pointed out that this is a Kronecker delta. Yeah, this is a Kronecker delta. It is not the Dirac delta. So again, you will see that this dynamics will involve the transport coefficients, right? So we have done that, and RA is defined like this. The initial heavy quark distribution function and tau naught, and then you evolve it through Langevin, and then you obtain a distribution, and then you take the ratio. So this is a very simple way to, read out RA. So that is our RA here. So if you just look at the RA, this is the plot that you get, RA as a function of PT. So the first one is, okay, radiative without this anisotropic part. This is with anisotropic part. There is something that you can see here. So for that, we have fixed these values. So these values are chosen to see the maximum effect here. So with these values of the magnitude of psi and this theta n, we can see this difference. Okay, so RA is basically kind of suppressed when you basically when you ignore the anisotropy. It is suppressed more. Anisotropy is kind of basically decreasing the suppression. Here it is like collisional plus radiation. I think both the contributions has been added here, and this is the plot of RA that you get. So these are very preliminary results in my opinion. So to make them more concrete, you need to work out to go into 3 processes in the presence of anisotropy, and also couple this analysis with hydro, and then you will be in a situation to compare these numbers with the experiment. Okay, so yeah, that's all. What now? I'll just tell like what we have discussed until now. We studied heavy quark drag and diffusion coefficients in an anisotropic medium. So momentum anisotropy in the medium leads to 2 independent drag coefficients and 4 diffusion coefficients, all of which depend on the angle relative to the anisotropy direction. So this is general argument. It has nothing to do with small or large anisotropy. So this will happen in general. How will you compute the transport coefficients? That complication is there, okay? So then we analyzed the radiative contribution to drag and diffusion, and we looked at them in contrast to the collisional ones, and some crude estimate of RA also has been made here. And what we realize in all that is that the angle between the heavy quark momentum and the direction of anisotropy contributes quite significantly. And strength of anisotropy, we don't have much scope to look at that. Okay, 0.2 and 0.3, they may not make much difference if there is no like complicated dependence there. Okay, so with that, I think I will just conclude my talk by saying that we will, in our future work, will include coupling this framework with the hydroevolution, and we'll have to do all that. So it will take a bit time. So we have some experience in connecting this with hydro. We work with the music. I think you must be knowing music in Martini codes. I think Manu did that but without anisotropy and magnetic field. And then we have recently developed a hydro based on momentum dependent relaxation time. And we would also like to model our background medium with the help of that. So what would be the effect of momentum dependent relaxation time that will enter in terms of the corrections to the distribution functions? That also need to be looked at. Okay. So hopefully, if we make some definite progress, we will be able to compare these results with the experimental predictions, and we can say more concrete things on that. This is another direction where the inclusion of electromagnetic fields, how much these fields will contribute, that is a matter of debate, but there are initial large transient magnetic fields that could be there, and their decay time may be enhanced by the medium conductivity, but again, that may be for few, like maybe 2.5 Fermi per C or 3. We have to see whether they may contribute or not. We have again made some initial studies where we develop a method to include the strong field effects and also weak field effects in some of the works. And maybe we will see like whether we have some way to include some kind of space-time dependent electric and magnetic fields in the analysis or not. And also, of course, the radiative contributions need to be relooked at in the magnetic field. Okay, so these are some of the ongoing works or discussion at the level of discussion stage with my collaborators Santosh, and maybe we will come up with some more results here, and we'll be able to make some more concrete statements in this direction. Okay, so with that, thank you very much.
Thank you, Vinodji. Any question?
So the studies that you're doing are more relevant for the proton ion collisions, right? Because in central collisions, I guess central lead or gold, the anisotropy decreases very fast, right? Because the hydrodynamization starts from.
So right now we didn't think in that way, but now we have to relook everything basically. Earlier, most of these studies were based on the uniform field. I mean, and field will not remain uniform, right? Most of the studies where like the Landau, you include the Landau label and then you sum it, and then you also know how to do, scattering things with constant field. So this was, most of the works were done like that. And you know that field, that strength will not be constant. So it is a transient magnetic field, it will decay. So that part need to be looked at.
Yeah.
But
And also, I was wondering whether this temperature that you quote here, that is relevant for the P gold collisions, or?
This is some sort of initial temperature, but it is like little bit more than what it is, right? So right now so these are some numbers that we could, like some initial temperatures that we could see, because I think the anisotropy may be relevant there, right?
Yeah, because central
so-
collisions, most probably it is
Yeah, it
now.
will not be there
Yeah, the
initially.
anisotropy goes very fast.
Yeah, and I think it will grow through the hydro, but in the late stages, and that is different kind of situation. Yeah.
Any further question?
So, okay. Okay, 360. I think some initial energies, maybe the onset of hydro, and that is the kind of temperature that, yeah.
Just a basic question. So generally people treat the heavy quarks evolution non-relativistically. So what are the challenges of doing it relativistically in a normal fashion people do for other particles?
So here it is non-relativistic only, right? I mean,
yeah, I'm asking for what are the challenges if one wants to expand it in a relativistic.
Oh, due to their mass, I think the relativistic effects, even if they are there, even let's say for charm quark, they will be very minute, right? They will be very small. So you can always go to like 1/m corrections and then, do something. That you can do, of course, within some effective field theory.
If one goes to higher energies in future, then?
Maybe. I don't know whether these approaches, how will you use them? I don't know at this moment. So I don't want to, I just don't want to comment on things based on this approach. But of course, the relativistic effects you can include, order by order, 1/mq, 1/mq square, right? And for charm quark, I think this charmonium velocities are maybe around 0.25 to 0.3. They may be relevant for that, but for bottom and all that will not be relevant. So I don't know how to include it within this framework. That I don't know.
Okay. Yeah, I mean, you can discuss if you have any further question. And let's thank Professor Vinod Chandra.
Okay. Thank you very much.